12.11, three 170-gram masses in figure 1 right here are connected by massless rigid rods. A, what is the triangle's moment of inertia about the axis through the center? So this is figure 1 here. We have a equilateral triangle around an axis in the center. All of these little balls are 170 grams, and we're going to pretend like there's a rods connecting them that we're assuming to be massless. So to find inertia, we use the equation mass times radius squared. Mass, right? We're going to do this in kilograms. Kilograms meters. Kilogram meters is the unit for inertia. So we convert the 170 grams to 1.7 kilograms, and then we're looking for R. So it's kind of, first you might look at R and you might say, oh, is it 40 centimeters? It's half of 40. That's there. But we can also look at this simple way, knowing that these are all 60-degree triangles, and we can make a 30, 60, 90 triangle, X. So the 30, X to the square root of 3, X and 2X, which, right, to 30 is X, 60 is X. And we'll know that this right here is going to be 30 because we're going to cut it in half, right? We're going to cut it in half to make a 30, a 60, and a 90 here. So we'll do 0.2, because we know 40 centimeters, so in half is 0.2, is equal to X square root of 3, divide that by square root of 3, and we get X is equal to 0.11543, and then we'll multiply that by 2, because the 90, the radius is going to be this right here, and we will get our radius as being 0.23 meters. And then we can just plug that back in, and we get the answer, 0.0272, or 2.7 times 10 to the negative 2 kilograms times meters squared. Pretty simple. For B, what is the triangle's kinetic energy if it rotates about the axis at 5.2 revolutions per second? So the equation for kinetic energy is equal to 1/2 inertia times omega squared, the angular velocity. So how fast is it going around this center? And we know that's 5.2 revolutions per second. But I want to stop and think, because omega, angular velocity, is in radians, and this is giving us our revolutions per second. But this is telling us how much it goes around in radians. So we want to know, so we want to convert this to radians, and we'll do that by multiply it by 2 pi, because it's going around like in a circle. It's going in a circle, right? So it's telling you how many revolutions, but one revolution is one time to go around. And one time to go around a circle is 2 pi. So we do that 2 pi times the frequency will give us omega, and that ends up being 32.6728. And then we plug that back into this equation, 1/2 inertia times angular velocity squared, and we get 15 joules, which is joules is the unit for kinetic energy, for all energy. So thank you.